Well, let's go ahead and get started. Welcome back to another Chem 400 lecture. I want to show you the website, the Chem 400 website, what everything is there. I did just post for Monday and Wednesday the lab 4 values for the ideal gas constants. I hadn't realized this before, but apparently we have a Jason and a Jeff on Monday, and they also paired up on Wednesday to be a lab group, and so there's a Jason and Jeff on Wednesday. So anyway, that's what I learned from typing in the values. Jeff?
Jason wanted me to tell you he's tired of pop, but he sent an email with his discussion question.
Thank you. Yeah. See, true partners there. Right? Yeah, the other thing I guess I learned is that experiment 4 works, right? Because everybody, or almost everybody, got a value close to 0.08206, or reasonably close. Anyway, there's lots of stuff here, companion notes, lecture note companion problems here. Chapter 8, which we haven't even gotten to yet, doesn't have any companion problems. Otherwise, they'd be there. Right at the top is the lecture videos link posted on September 10th. And if you don't find the discussion section assignment, if I forget after today, after Wednesday's discussion to post it after 4 p.m., just remind me and I'm happy to post it. So sometimes I do forget. Okay. Well, where were we? We were talking about these things called ideal gases and the kinetic molecular theory of ideal gases. We say gases are comprised of particles that are flying around very fast in their containers. This explains why they fill the entire volume of the container. The size of the particle is negligible compared to the volume of the gas. What percent of the volume does argon take up? 0.01%, so a very tiny percent of the volume. And a couple other things I want to say about this. If I can find my notes. That was number 1. I gave you number 1, right? Did I give you number 2? No. Number 2. We'll pick up right where we left off. This explains why gases have such a low density and are so compressible. This explains why gases have such a low density and are so compressible. I don't know if you remember me saying this at the beginning of Chapter 5, but at the beginning of Chapter 5 we said that our picture of a gas is that if you look at the diameter of the gas particle, the next gas particle is approximately 10 diameters away, or 5 or 8 or somewhere around there. It depends on the exact pressure, of course. But as far as a rule of thumb, if you think about the fact that for liquids and solids, the next particle is within a diameter, and then these are 10 diameters away, and you think about 10 diameters in the x, y, and z direction, 10 times 10 times 10 diameters. There's about 1,000 times more space in a gas than a liquid or solid. And that's why gases have densities that are approximately 1/1,000 of a liquid or solid. And that's the next point. So gases have densities approximately 1/1,000 of solids and liquids. One 1,000, and that comes from that 10 diameters in each of the x, y, and z directions. 10 cubed is 1,000. for 1/1000. We're going to sneak one more in there, that's number 4. Number 4 is going to say that for a truly ideal gas, each particle has no volume. And what we're getting at is we're getting at this idea of what does it mean to be an ideal gas. An ideal gas is a limit. And that limit includes the fact that for a truly ideal gas, each particle has 0 volume. And therefore, the gas particles in a container take up 0% in that analogy. And of course, we know that that's not true, but we also could guess that that's pretty close to true. Okay. So we know that the volume that's open is 99.99%. Question, Brenna? Repeat 1. 1. For argon gas at STP, 0.01% of the volume of the gas is particles. I don't know if I exactly said that, but something very close to that. And so sometimes questions come up. Let's say this. We're dealing with ideal gases and the ideal gas law. And at the end of this chapter, we're going to deal with non-ideal gases, also called real gases. And we will account for the volume of the particles. That's what we're going to do. Anyway, so we'll see that coming up. All right. Next slide. The collision of one particle with another or with the walls of the container is elastic. This is actually a physics term, but an elastic collision is a collision with no loss of energy. So that's a definitional thing. And our picture, at least, of what's happening is these particles are coming together at hundreds of meters per second. That is today's demonstration, by the way. And it wasn't even hundreds of meters per second, but it turns out that when a collision occurs, it's occurring very fast and without loss of energy. And well, now let me talk about this ideal gas, this truly ideal gas, for a second, and then we'll come back to elastic collisions. For a truly ideal gas, there are no intermolecular forces and intermolecular forces, abbreviation, we won't study this until chapter 11, but the abbreviation is capital IMF. For a truly ideal gas, there are no intermolecular forces attracting gas particles to one another. For a truly ideal gas. And so our picture now, hopefully, that of an elastic collision, it's going to be a collision that occurs so fast that if there if there were intermolecular forces, they were not important, okay? And so you can imagine, perhaps, H2O gas and another H2O gas. Does H2O have intermolecular forces? Some of you may know this. Yes, it does. Do you know what kind of intermolecular forces it has? Has hydrogen bonding, has other ones as well, but that's a pretty strong one. But what's going to happen is the collision is going to occur so quickly that whatever force of attraction there is negligible. And in the limit of that, for a truly ideal gas, we say there are no intermolecular forces. Okay? So, let's see. For truly ideal, there are no intermolecular forces attracting. And the gas particles are moving so quickly that this is true, or this is essentially true. But that's why do collisions occur with no loss of energy? Because gas particles act as if they have no intermolecular forces. This is kinetic molecular theory, and each of the A, B, and C parts of it explain something about gases. This explains why gases exert pressure due to the collisions of the gas particles with the walls of the container. So what I'm going to write explains pressure of a gas due to gas particle collisions with walls of container. Last but not least, the average kinetic energy of a particle is proportional to the temperature in Kelvin. And I put this up in lecture before. Now we're going to talk a little bit more about it. I said KE, that's kinetic energy. Bar means average. Average kinetic energy is proportional to temperature. We're going to state that. We're not going to prove that. That is true. It is provable, actually. But if we accept this, then we can do it and use another equation. And the other equation perhaps is more familiar for those of you who have taken physics at some point. This one says that the kinetic energy equals 1/2 mv squared. M is mass, v is velocity. And to make these equations more similar, I'll put a bar over this to make it average. And it'll turn out that the velocities will be averaged. And we'll talk more about that. But that's where the bar goes. And so now, I'll combine these two. And say that 1/2 mv squared is proportional to t. And we'll take a couple statements about that. First off, as T increases, so does the average kinetic energy. constant T as the mass of the particle increases, the velocity of the particle decreases. Still proportional as one goes, so to maintain proportionality, if one goes up, the other one has to go down. Heavier particles are traveling more slowly. Still probably traveling 100 meters per second, say for a couple, or 500 meters per second for an oxygen molecule, that's O2, whereas a hydrogen molecule, H2, probably traveling closer to 2,000 meters per second. They're all moving fast. The question is how fast. All right. Yeah, let's move on. I think I have more to say, but we'll say it later. Next, oh, I guess technically this is 5 now, but I'm going to just leave it. Gas particles have a distribution of kinetic energy values called the Boltzmann Distribution that is the same for all particles at the same temperature. A Boltzmann distribution, that's what I'm about to draw for you, commonly drawn or interpreted by you on the second exam. Those of you who have had discussion have run into these already. Those of you who have not are about to run into it. The y-axis is F, where F is the fraction of molecules with a particular kinetic energy. And the x-axis is kinetic energy. Let me draw one of the curves, and let me draw another one of the curves here too. And you'll notice that these have no axes, no numbers on the axes. They do have axes, but no numbers on the axes. These are qualitative pictures. This one here is lower temp. I'm going to assign it to 300 Kelvin. The red curve I'm going to call 600 Kelvin. And now I will discuss. So, first thing I want you to know about these two curves is that at any temperature, there's a distribution of kinetic energies for gas particles. At any temperature, there is a distribution of kinetic energies of gas particles. Now, on the previous slide, what I said was that average kinetic energy is proportional to temperature. What that means is that if temperature doubles, average kinetic energy should double. Yes. We should understand this. Now let's talk about what the average is, and I'll zone in here on a couple points here. Before I do the average, let's do the most probable. The most probable has the highest fraction, and therefore it is the highest point. So I'm going to write right here, most probable. And it is, in fact, the most probable kinetic energy. I'll do the same thing for 600 Kelvin. It has a most probable. It's the top. Now let's focus in on the black curve here for a minute. The black curve, if I were to ask you to take the average kinetic energy, you would say, well, there certainly are a lot, there's like a long tail out here. That's going to move the average from here somewhere over on this side if you were to average all these numbers. And we don't have to know exactly where. All you do have to know is that the average is somewhere to the right of the top, due to the fact that you're averaging all these higher numbers out here. So let's do blue. Actually, I didn't do a bad job here. 300 Kelvin, well, somewhere right around there. The blue marks are the average kinetic energies. And again, all you have to know is that it's somewhere to the right of the peak. And I don't know, my curve isn't that good, but if you look at whatever the number is here, and you look at it is approximately double the kinetic energy. And that is true. Kinetic energy, as temperature doubles, average kinetic energy doubles as well. And so if I ask you to draw these curves on homework 5 or on your exam, that's the kind of thing you'd be looking for to draw approximately. All right. Next point. This 300 Kelvin curve is the same for all gases. All gases have the same Boltzmann, or the same distribution of kinetic energies at the same temperature. So I'll write here B. All gases at T equals 300 Kelvin have this curve. Have the black curve of kinetic energies. Now, what does this mean? There are a variety of kinetic energies, some of them very small, some of them very large. If something has a kinetic energy of 0, what is its velocity? 0, goose egg, donut, yes. So inside this room, where there is a gas, is it 300 Kelvin? That'd be 27 degrees Celsius. If we leave this little guy on our projector, it's going to heat up the room enough that it might be by the time we leave. But what we're saying is that inside this room, maybe it's a couple degrees lower, but it's the same idea. So there are particles that are stopped. And there are particles that are moving at 3 to 4 to 500 meters per second. And they are colliding. And if a particle 0 and a particle 500 meters per second collide, it will be elastic, meaning that there will be no loss of energy. There can be transfer of energy, and so they could each be going 250 when they're done. And then it bumps into another one and transfers energy. And let's say this one's going in this direction, and this one's going in the other direction, and this one almost stops, and this one zooms up. They're allowed to transfer the kinetic energy with no loss of kinetic energy.
Average straight line.
the average is this point on the curve. And the average depends on which curve it is. But there are a variety of speeds. And what we tackle in discussion this week is we then prove that the area under these two curves is the same within our ability to cut. And then, exactly, well, my drawings may not be perfect, but when I actually plot them out for discussion, you'll see that is true. And that's just based on the fact that all the fractions have to add up to 1. So, and then what we do is we deal with the fact that as you go to high kinetic energies, there are exponentially more high energy particles as temperature increases. And that will turn out to be why you get exponentially faster reaction rates. And reaction rates is a Chem 401 topic, so we're hedging our bets here. Right, so it's like a teaser. Bodie?
What's the significance of 300 degrees Kelvin?
What's the significance of 300 degrees Kelvin? None, other than it's about room temperature, and I just chose 300 and 600 to show you the doubling effects.
Okay.
Could have been 250 and 500 as well. Let's see. Yeah, at any temperature, there's a, so this curve could be the curve for nitrogen at 300 Kelvin. It is also the curve for oxygen. It is also the curve for popcorn smell. Whatever, I got to look that up, by the way, because I say that. It definitely has a structure somewhere, but I'll look that up. But and at 600 Kelvin, they're all the same as well. And what I'm going to do for you, though, is I'm going to get to a curve where they're not all the same. And so let me emphasize this. Fraction and kinetic energy on the x-axis. I'm going to change the x-axis coming up. I won't change the y-axis. Maybe even right now. Oh, I don't think I'm quite ready yet. Oh, yes I am. Good. Now all the curves have changed, are different. But all gases have different masses and therefore different velocities at the same temperature. So this is all at the same temperature. I don't think it says what temperature it is. I think it's room temperature. But all I'm going to say is all gases at the same temperature. And this gets to the fact that the equation that I gave before like this, and the idea that as mass increases, velocity decreases. Still a distribution of velocities. Same T, as mass of gas particle increases, velocity decreases.
Is it because of gravity?
Just a second. Is it due to gravity? No. Ideal gases act as if gravity has no effect on them. There are no intermolecular forces. They are flying free, even of gravity, even of intermolecular forces. But if the question then is why is this, it's because the kinetic energy is the same for all these gases. Kinetic energy equals 1/2 mv squared. So if they have the same kinetic energy, then as mass goes up, velocity goes down. And these are, I believe this is room temperature, I'll have to double check. the molecular velocities in meter per second. You can see oxygen, a range of velocities, an average of a little less than 500 meters per second. H2O, a little bit lighter, a little bit faster. Up here, now it's time for me to give you the equation for the velocity. The velocity that we calculate is called the V sub RMS. That is going to be the root mean square velocity. That has to do with the fact that this is squared right here and we're taking the square root of it. Equal sign. Square root of 3 RT over molar mass. Let's see. T has to be in Kelvin. R has to be 8.314 joules per mole Kelvin. And MM is molar mass. Now, we're talking about velocities, and when you use this equation to get kinetic energy, the mass here, which doesn't have to be the molar mass, the derivation of this has to be molar mass, but the molar mass has to be in kilograms per mole. In kilograms per mole. So you have to do the conversion from grams per mole to kilograms per mole. Let me do that down here. O2, the velocity root mean square, using this equation. We'll do it at 298 Kelvin, room temperature. It's about 298. And then O2, that's 32 grams per mole, that's 0.032.
They say kilograms.
0.032 kilograms per mole. Calculate this all out. 482 meters per second. Is the root mean square, or what is sometimes called the average velocity of gas particles of oxygen. So that'd be right about there on the red curve for oxygen. So they're moving right along. This equation is given on your conversion and equation sheet. You'll see some homework problems about it, so you get some practice. We won't derive it. If you want to talk about the derivation of that, we can do that in office hours. It's not significantly helpful in the exam.
How many miles in a second is it? That's a lot.
Meters per second? Yeah. That's fast. So there's oxygen in this room, right? 482 meters per second. In theory, if it didn't collide with anything but the walls of the room, it would go back and forth a couple hundred times per second. But even at the densities that we said, so 10 diameters, there are still a lot of collisions. So it doesn't make it right. But yeah, that's so I don't know. I don't know how many meters per second that is, other than a lot. Given two corked flasks with the same volume temperature, one has 0.2 moles of oxygen, another has 0.2 moles of argon. First question we're going to ask is, which has a higher pressure?
Argon. Argon.
Let me put up an equation, and then we'll discuss.
We know.
Volume and temperature are constant. Moles are the same. What can we say about their pressures? The pressures are the same. Okay. And so whenever you're thinking, and I know we're going to talk about kinetic energy here in a second, but we're mixing it up with pressure a little bit. So these two gases, and any gas with the same number of moles, acts exactly the same. That's one of the points of the ideal gas law. Same. Let's see, and we came back to one of the few equations, or one of the, I guess, 5 equations this chapter. PV equals nRT. So volume and temperature are constants. That means that pressure and moles will be proportional. Same, and all gases act the same. All gases act ideally, according to the ideal gas law. So I guess my note here will be same moles proportional to pressure. When volume and temperature are constant. Which flask has particles with higher average kinetic energy? Well, for this one, average kinetic energy is proportional to temperature. Temperature is the same. We can say that your average kinetic energy is the same as well. Now something will finally be different for C. Which flask has particles with a higher average velocity? That one comes back to over here. We know that at the same temperature, if it has more mass, it'll have lower velocity and also lower average velocity. So argon versus oxygen. Oxygen, 32 grams per mole. Argon, almost 40 grams per mole. So oxygen has the higher average velocity. O2?
Slightly.
Slightly, yes. Oxygen has higher average velocity because it has smaller mass. And on your homework, if I ask you what is the answer, and then I say why can be a sentence, why can involve an equation as well, something that tells me that you've related it to the properties. Any question about problem number 6 here? And let's move on to problem number 7. Given two corked flasks with the same volume temperature, one has 0.2 grams of oxygen, another has 0.2 grams of argon. Now, which flask has a higher pressure?
Argon has more moles per gram.
Well, let's see. So we come back to this. And then, and on an exam or on a homework that you get this equation, you just say, well, if I need to know how many moles there are. I know how many grams there are. I know how to do the conversion. So, like, I think there are many ways to solve these problems. There's the more intuitive approach, and then there's the more calculations-based approach. And then, of course, there's way 3, which is brute force memorization. But there is so much crap to memorize in this class that I would suggest you try plan 1 or plan 2. Anyway, but if you have the same mass, we just said that argon had a larger molar mass. Therefore, you're going to have more moles of oxygen. More pressure of oxygen as well. Any questions about that? Which flask has particles with higher average kinetic energy? Well, average kinetic energy, you're always, as soon as you see average kinetic energy, you think temperature. Temperature's the same. Average kinetic energy is the same as well. And it's the same explanation. And temperature is constant. Which flask has particles with the higher average velocity? This one comes back to the same one as C. So there are more particles, but there are also particles with a higher average velocity. Same reason as 6. Any questions about that? Good. Okay. What's the other possible x-axis? This is molecular velocity. What's the other one I just showed you? The other one I showed you is kinetic energy. When kinetic energy is down here, all gases have the same curve. Anyway, that's in your notes too, but I thought I'd say it one more time. Draw a Boltzmann distribution using molecular speed on the x-axis for methane and neon at the same temperature. Methane, well, so if this was on your exam, I would give you the formula because there are no nomenclature questions on your second exam. Neon's just... We have a molar mass of 16, molar mass of 20.18. Actually, I think it's 16.04. I apologize for this. I've tried to eliminate molecular speed because I haven't shown you. Did the last one say molecular speed? Shoot. I said molecular velocity. What's the difference between speed and velocity? Velocity has a direction. Are they the same number? Yes. The difference between speed and velocity is that speed would be 55 miles an hour. Velocity would be 55 miles an hour.
South.
South. West. No. North. There we go. Yes. And so, anyway, I went back to this. I apologize. I'm going to use the term velocity, so don't worry about speed. We don't have to, so speed, that's a movie. All right, so which one has a, well, we would draw this. The y-axis is always f. F stands for fraction of particles with a particular velocity in this case. Still no numbers on the y or x axes. Still nothing up my sleeve. Which one's this one? This curve. This curve has to be neon. Now what will happen is, when, for those of you who are going to do discussion after today's lecture, you'll see that the curves are actually much more similar than I'm drawing them. Feel free to space them out as much as I do to make it obvious what the answers are. Like, you don't have to make them, I don't know, like, on the discussion, one of them will look like this, and the other one will look like this. And you're like, and it even looks closer than that. Anyway. Any questions about this? Pressure and temperature, a molecular view. I'm going to give this molecular view one slide. There's actually much more to it, but I taught it once and it sort of went over like a lead balloon. But there's a branch of chemistry and it's related to physics, and it's a branch of physics as well. It says, what if I had a particle in a box with a velocity x? Can I actually derive something like the ideal gas law just from looking at a particle in a box? And you could make a couple of assumptions. One is that that particle has no volume, and another is that it has no intermolecular forces. You'd be right. Those are the kinds of things that you're assuming. We're going to talk just about a couple things. The box is length L. The particle is moving with a velocity x in the x direction. First thing I want to ask you is, when the particle hits the wall and bounces off, what is its change in velocity? When the particle hits the wall and bounces off, what is its change in velocity?
Cancel.
And here's where we need velocity and not speed, because the collision's elastic, the wall's not moving, and so when it collides with the wall, if it's moving at 1 meter per second, it is now moving with 1 meter per second, but in the opposite direction. So if you just looked at speed, you would say 0. But if this were, well, let's do it like the particle is. So let's call this particle, this direction, positive, moving at 1 meter per second, and then it bounces off and it's moving in the other direction. It's actually Vx minus Vx. So the change in velocity, if I'm moving 1 meter per second this way, and then I'm moving 1 meter per second that way, I have actually changed by 2 meters per second. My velocity when I'm hitting the wall is still 1 meter per second, but in the opposite direction. That's why it's minus Vx. And the two minuses cancel, and so the change in velocity is 2 times Vx, whatever this velocity in the next direction is. Okay. Let's try one more. Let's ask the question, how long does it take the particle to go from down to one end and back again in the box. How long does it take to go from here down to one end and back? Leo?
Is it 2L over V?
2L over V. So the length, it's going to be length divided by how fast you're moving, right? If I'm moving 1 meter per second, well, wait a minute. I'm going to turn it on some first. No. I'm going to bounce off the wall. All right, how long did that take?
Twice as long as the last one.
It depends on how long it is and how fast I'm moving, right? And so, Leo, you've got it. It's 2 times the length divided by my speed. The speed of this particle is, we're calling v sub x. Now, so now we'll touch base with these equations. Force equals mass times acceleration. Are we okay with that? How many people have seen that before? How many people have not? How many people are refusing to raise their hand? All right, well, maybe it's familiar. Then acceleration is change in velocity over change in time. So we plug that in. Our change in velocity is here. Our change in time is here. And what I've done is for delta V, I've put in my 2Vx. For delta T, I've put there. My 2's cancel. And the L stays down, but if you're in the denominator, you come back up. And now we have an equation for the force of the collisions on this wall as a function of just mass and velocity of the particle in the box. And from there are several more steps that I will skip. There are several things up my sleeve today, and but you can derive the ideal gas law from arguments like this. Anyway, that's all I wanted to say about that. But there is a branch of chemistry, just like start with a particle, figure out the ideal gas. To be honest, not on the exam. But interesting nonetheless, and so that's why we show you. All right, and so from that you can get this equation for the root mean square velocity of a gas particle. We did one example, we'll do another example. What do we get for the root mean square velocity of a molecule of O2 at 298 or 25 degrees Celsius? 480, I think. 482. What would we do, right? .314. This joules per mole Kelvin. This time 273. Lower the temperature by 25 degrees and you get 461 meters per second. So it slows down. The other problem is a companion problem. Any questions about this? Okay. Diffusion and effusion. The process of a collection of molecules spreading out from high concentration to low concentration is called diffusion.
Weather patterns.
What's that?
Weather patterns.
Weather pattern, yes. Well, weather is a big topic. And the idea here is that the smell of a warm cup of coffee diffuses throughout a room. So does popcorn, by the way. Process by which a collection of molecules escapes through a small hole into a vacuum is called effusion. Have you ever done the experiment where you took a drop of ink and placed it into a cup of water, a glass of water? That would be diffusion. But first thing I want to say about these two processes is that diffusion and effusion are governed by the same types of equations. They are in effect the same processes, or based on the same processes. It turns out that effusion is much easier to set up an experiment for. And therefore we will have Graham's law of effusion. We will not talk about any equations for diffusion. They're more complicated. Typically you're diffusing in 3 dimensions. Here you're diffusing through essentially one dimension. The equation looks like this. Rate of gas A divided by rate of gas B is equal to the square root of the molar mass of B divided by the molar mass of A. And so I do have it correct. On one side, A is in the numerator. On the other side, B is in the numerator. Question, how much faster will oxygen diffuse or effuse? Like I said, this is an equation for effusion. They're governed by the same types of equations. Effusion is just much easier to study, but the process is the same. Going to have the molar mass of argon on top, 39.95. this is oxygen gas, and so it is O2. And I get 1.12 times faster. And really 1.12 is your answer, because if you said rate of diffusion of these two, it's equal to 1.12, but our point is that it's actually faster diffusion for the two. Questions about this? This equation is, should be on your conversion equation sheet as well. Sorry, before we move on, oxygen or argon, which one's moving faster? Whichever one has the lower molar mass, right? And so this Graham's law of diffusion is related to the fact that oxygen is moving faster. If it's moving faster, it'll have more collisions with this wall. Those collisions, on average, will create more of the oxygen molecules going through. It's not a size issue, because oxygen and argon in the ideal gas limit are essentially zero volume particles. So, anyway,
Because the oxygen creates more collisions with the wall, and the odds are better that it'll hit that spot.
more collisions, more chances to go through. Yeah. All right, now we can move on. Okay. At STP, most gases are pretty close to ideal. You'll be calculating the molar volume of hydrogen gas from lab. You'll be doing it STP. 22.41 is perfect. I will say this for everyone, although I've told some of you already. In order to do this for lab, you have to do a combined gas law calculation to get to STP, because your experiment was not done at STP. Happy to help you with that. But anyway, so you can see there are small variations, but pretty much everything is very close to ideal in the molar volume. That's at least one measure of the molar volume. So now the ideal gas law assumes two things. First one is that the volume of each gas particle is 0. And the second is that there are no intermolecular forces. No IMFs, and I guess how I'll put it is no IMFs between gas particles. At low temperatures and high pressures, gases act less ideal. It's not an English class, but less ideal aid. At low temperatures, the speed of the particles is slower. Is that an okay statement? Temperature is proportional to kinetic energy. Lower the temperature, lower the kinetic energy, lower the velocity. Okay. So here is a high temperature collision between gas particles. Here is a low temperature collision. Hey, how you doing? Oh, pretty good. How about you? Yeah, I'm having a nice day. Oh, so interactions are important. Intermolecular forces are important. Ah, no wonder they act less ideal. At low temperatures, the speed of the particles is slower. The particles are close for a longer period of time. IMFs are important. Particles are close together for a longer time during a collision. IMFs are important. And now IMFs are keeping the molecules attracted to each other. These are attractions between the different particles. Do you know what the ultimate non-ideal gas is? It is a liquid. Because for liquids, they're like, hey, how you doing? Oh, nice. Hey, oh, that's hydrogen bond. Yeah. And then they're really important, right? Because they're together always. Ultimate non-ideal gas is a liquid. Where IMFs are super important, they're so important that liquids so complicated, we're not really even going to talk about
Do we know if when gas particles collide, I thought they were like billiard bars fall instantaneous, whether it's slow or not. But I didn't think that the impact duration varied.
Does the impact duration vary? I think
With speed of collision.
so. For the gases in this room, nitrogen, oxygen, argon, carbon dioxide, at room temperature and pressure, everything acts ideally. Not important. We're talking about what if you get lower than that? Certainly at some point, they will be moving slow enough to matter. And where we're going with this, by the way, and where we get to by chapter 11, is that there's a war going on. And that war is between temperature, which is always adding energy and always trying to break things up, and intermolecular forces, which are always trying to bring the particles together. They are forces of attraction. And so when we get to chapter 11, what we're going to say is that the higher the boiling point, the stronger the intermolecular forces, because these intermolecular forces are keeping them together to a higher temperature. Because ultimately, you get to a high enough temperature, say the sun. Everything's a gas. Iron, a gas in the sun. Right? So ultimately, you get to a high enough temperature, everything becomes a gas. And then that gets more complicated too, because all of a sudden electrons are flying off of iron and things like that. But the duration does matter at some point. And that's all we're saying is not for gases in any temperature and pressure that we deal with them regularly. Although I have to say, it's been cold. My little tire pressure sensor went off and said I have low pressure. Did that happen to anybody else? Yeah, one. Because in a very real way, temperature decreases, we will see that the pressure decreases as well. All other things being the same. And you want to know what I'm going to do when I go home today? I'm going to hook up my bike pump to my car, and I'm going to pump it up, because that's the only pump I have. All right, so high pressures, the particles are forced closer together so that IMF are more important. again, so now instead of being like this, and they have a collision, now they're like this, and like, oh hey, oh hey, oh hey, oh hey, oh hey. And there are more often collisions, and then the intermolecular forces are more. So really, either way, particles are closer together. Intermolecular forces become more important. Particles are closer together, IMF are more important. And perhaps you're feeling like the IMF, like I feel about the IMF, the the International Monetary Fund. I'm like, I don't know what that is. We haven't even talked about intermolecular forces in this class. So, but they seem to be playing a large role in our discussions. The van der Waals equation. Okay, so the van der Waals equation is an equation for non-ideal gases. So it accounts for the non-ideal behavior of gases. And interesting, let me see, is this the last slide you guys have?
Yeah.
Yeah, that's good. Okay. We have about 10 minutes, 8 minutes. We have about 15 minutes left. So. Accounts for the non-ideal behavior of gases. There are actually many equations like this because it's very important, especially to chemical engineers, to understand gas behavior, because if you don't understand it, that's when things explode. Pressures become too high. And so there are actually many of these, and I had a whole course just on studying the non-ideal behavior of gases and modeling it with equations. But what people found is that compared to ideal gases, the pressure was actually a little low, so you could add a term to it to get back to the ideal gas. And the volume was a little high, so if you subtracted off a term, you could get back to ideal behavior. And this is what's called an empirical equation. Empirical means you fit it to actual data. That's what engineers do. And you come up with an equation that describes it. And then you say, well, what's the theory behind it? And in general, the theory sort of goes like this. We assumed that the volume of the particles was 0, and that each gas particle had the entire room to travel. That's not true. There are other particles in the room, and so each particle has a slightly lower volume to travel. That's how we account. So each particle has a little less than the total volume of the room to travel. I said total volume of the room. I guess I should say container, because most gases are in containers. Most people are in rooms. This is the wall. Here's a collision happening with the wall. Here's a particle. Okay. So they found that if you add a little to the pressure, that the pressure actually worked out to be similar to an ideal gas case. And the idea is that when intermolecular forces are important, they will pull this particle away from the wall of the container just the tiniest bit and lead to lower pressures. So by adding a little bit back here. So what people say And I treat this as totally an empirical equation that fits the data, but you can theorize that this part adds a little pressure to counteract the effect of IMS, or to account for IMS. So let me say that, to account for IMS. I won't ask you to remember these two parts, meaning how this equation works. The last problem on the exam, on the homework 5, the 5-point additional homework assignment. Remember, this week's homework is worth 15 points. The last 5 points, because it's a 5-point assignment, cannot be dropped. So it's already so it'll be part of your grade. But here's what you're going to do. So, and it says this right on your homework. Let's call this D. You're going to solve the ideal gas law for, well, here's what the problem says. It says, a chemist wishes to study a gas blank. Get your gas name below. So, let's see. Alicia P. Peleni, right? P, you're going to be doing carbon tetrachloride. Carlos Calderon, you're going to be doing acetone. So you have to, everybody gets a different gas by their last letter. Then, why are these conditions where a gas would act non-ideally, blah, blah, blah. What is your gas's boiling point? You have to Google it. Use the ideal gas law to calculate the number of moles of your gas at 200 atmospheres. Is that a pretty high pressure? It's a pretty high pressure. And that's a pressure where gases act non-ideally. Solve the ideal gas law for your gas for the number of moles. And then you're going to use this, and it says this, use your ideal gas law estimate as a guess in the van der Waals equation. On the left-hand side. What's that?
PV over RT?
PV over RT. So this is just a rearrangement. PV equals nRT. What I've done is I've rearranged the ideal gas law, the van der Waals equation. To get n by itself on the right-hand side. You're going to put n from the ideal gas law into this portion of the equation. Your pressure is given, your volume is given, your temperature is 200 degrees above your gas's boiling. So you're going to solve the left-hand side for n. And let's say that your ideal gas law estimate of moles was 12.00. and you put 12.00 in here. Your A and B are on the last page of your homework. You got all the stuff. Let me know if you can't find it. Put N in here. And you say you put in 12.00, and you solve this whole equation, and you set it equal, and you solve it, and you get 12.45. These two parts of the equation are not equal. Therefore, it's not a true statement. So you take the number you get out, 12.45, and you plug it back in here for n. And you solve the whole thing again. And this time you get 12.56. They're still not equal, but they're getting closer. And then you put 12.56 in here. And you solve the whole thing. And now you get 12.59. And then you put 12.59 back in there. And you get 12.59. Then it's true. Then you're done. Maddie?
The first time around, are we assuming it's 0?
First time around, you have to use your ideal gas law estimate. Okay? If you try and put 0, or if you put any number other than the ideal gas law estimate, what can happen, well, let me say one thing. This is what's called solving a problem through an iterative approach. Each time you plug in n, it's called an iteration, and you're iterating it until it converges. And the reason you're doing that is because we have n squared times n, that's n to the third power, cubic equations. Well, if this was a quadratic equation, second power, you could use the quadratic equation solver. But here's what I need you to do, and I know I'm out of time. I apologize for going over. I need to see all of your n values for each of your iterations. Some people it will take 5. Some people it will take 15. Each gas is a little different. Good luck. Anyway, if you need any help with that, Emilio, question?
What does the B stand for?
What does B stand for? To get your A and B values, you have to go to the last page of the homework and it lists each gas has different A and B values. I do have homework 5 blank copies of it up here if you didn't get a chance to get it. We'll take a break. Lecture's over, and then we'll pick up discussion for those of you who have it at 2 o'clock.